In this video, let's take a look at an example for a one-sample hypothesis test for the mean when the variance is unknown and we're doing a right-tailed test. In this example, we're looking at reducing the time to process customer orders. So the organization is trying to improve quality throughout the total organization. Historical information indicates that it is a normal distribution with an average processing time of 4.6 hours. Management has reduced the process complexity and introduced new forms which should reduce the overall processing time. A sample of 16 was taken with a mean of 5.2 hours and a standard deviation of 1.2 hours. We're going to test the hypothesis to see if the time has reduced, and we'll use an alpha of 0.05. So a few things to point out initially in the problem. We're using a sample, which is how we know that this is the variance unknown version, and we're looking to see if the time has been reduced, so we're using the right-tailed test. Based on that information, we're going to set our null hypothesis that the mean, or mu, is less than or equal to mu naught. And the alternative hypothesis would be the opposite, which is that the mean, or mu, is greater than mu naught. Our alpha value is 0.05 based on the problem. Our mu naught was 4.6. Our x bar is 5.2. Our sample standard deviation is 1.2, and all of this was given to us from the problem. Our sample size, we had 16 samples. Our degrees of freedom, since we're using a sample, is our n minus 1. So we can calculate our value from our t-table using the function t dot inverse. Since we're looking at the right-tailed test, we're going to take the negative of the t dot inverse function, and then we'll use our probability or our alpha value of 0.05 from cell B20 and our degrees of freedom from cell B25. That gives us a t-value of 1.7531. So we'll use that as a comparison for our t calculation. For our t calculation, we're going to take our x bar value, which was 5.2 in cell B22, and subtract our mu naught, which was 4.6 in cell B21. We're going to divide that by our sample standard deviation from cell B23, which is divided by the square root of our sample size from cell B24. That gives us a value of 2.00. So graphically, we can look at our value of 1.75, and we can tell that our t calculation will fall to the right of that, which is in the reject region. So we can formulate this using conditional statements to come up with our conclusion. So in this case, if B26, which is our t-table, is less than B28, which is our t calculation, then we're going to reject the null hypothesis. And in this case, again, we can tell from our t value of 1.75 and our t calculation of 2.0, we should reject the null hypothesis. However, otherwise we would fail to reject the null hypothesis. In this case, we have the correct conclusion, which is to reject the null hypothesis. We can also calculate our p-value using the t.dist function. We're going to do 1 minus, since we're looking at the right side of the distribution. We'll use our value from B28, which was our t calculation, B25, which was our degrees of freedom, and then we'll use a 1, and that gives us a p-value of 0.0320. Since that is less than our alpha value of 0.05, we're confident in our conclusion to reject the null hypothesis.